Now it turns out that the electrons in atoms, so electrons and nuclei, aren't the only things that have these discrete values of energy. We say the energy is quantized. So quantized, what does that mean? One quantum is one packet of energy of a particular value. So one quantum of energy would be delivered here 3 eV by a 3 eV photon. It would deliver a 3 eV quantum. Well, it turns out that other kinds of internal energy for very small systems also are quantized, meaning these systems can have only certain values of K plus U. So let's take the next most complicated thing after an atom, which is a diatomic molecule. And not too surprisingly, we're going to consider the diatomic molecule to be something like two atoms connected by a spring, which is, of course, the chemical bond. So here's our diatomic molecule, and here's our potential energy curve for a mass on a spring, two masses on springs. And this line is basically the equilibrium distance, equilibrium separation. So this is a plot of potential energy as a function of the separation of the two things. It turns out that for this diatomic molecule, which of course isn't just sitting there, it's actually vibrating, that the vibrational energy, the sum of kinetic energy of the atoms and the spring potential energy, also can only have certain discrete values. So in the ground state, K plus U has, and it's negative, of course, so it's a bound system. So K plus U has some negative value. If we absorb a photon and put it into the first excited state, K plus U is larger. And the second excited state, the sum of kinetic and potential energies is larger and larger and larger. And we can't, and so how would you get it into excited state? Well, it could absorb a photon of the right energy, or you could collisionally excite it, same old way. How would it lose energy and go from this energy state back down to the ground state, say? Emit a photon. So okay, and notice notice some kind of interesting things about this. First of all, notice the spacing of the possible energy levels. They're actually the same. Okay, the spacing, unlike the hydrogen atom, if we look at the energy levels for what we call a quantum oscillator because it oscillates, of course, quantum because it only has, so we're getting into this oscillation business, huh? So it looks like as long as we're in this parabolic part of the potential energy curve, that this delta E between one level and the next highest level is exactly the same. And that's correct. Now notice that the way we've depicted this vibrating molecule here, a larger kinetic plus spring energy corresponds to a bigger vibrational amplitude, but not to a different vibrational frequency. And that's an idea that's carried over from our treatment of the classical mass and spring, the everyday macroscopic mass and spring that you experimented with in the lab and that we've looked at a lot here. And basically, so classically in our macroscopic world, for a mass spring oscillator, K plus U would of course be half mv squared for the mass plus a half K sub s squared, so that's the kinetic plus spring energy. And we know that we know that that's related, that's related to the amplitude of the oscillation, because at the farthest stretch, everything's potential energy. When it's not stretched at all, everything's kinetic energy. So if kinetic energy is 0, then the spring potential energy must be half K sub s times the maximum stretch squared, and the maximum stretch is just the amplitude of the vibration. So it looks like energy classically is proportional to amplitude squared, actually. And so we're using this sort of semi-classical picture here. Now, it turns out, and this is not something we're going to be able to calculate at this point, but we can accept it as a result. Where do we get the numbers for these energy levels and differences between energy levels? We actually get them from doing energy calculations. It's just that the energy equation for these microscopic systems is a little bit different than the energy equation we've been working with, because it has built into it this idea that it can only have certain values. It's called the Schrödinger equation, actually. And here's our ideal quantum mass spring system with these evenly spaced energy levels. And it turns out that this delta E, this E sub n minus E sub n minus 1, is actually related to the frequency at which this thing is vibrating. And it has the value, there's a constant times the square root of, what a surprise, the interatomic spring stiffness over the mass of the atom. So that's our omega for the small system. And we often write that as the quantity omega 0. So that's the interatomic spring stiffness over the mass. Okay, so you can see it written as this funny constant, h with a slash through it, omega 0. And what is this h with a slash through it? H is called Planck's constant, named after Max Planck. And it has the value of 6.6 times 10 to the negative 34 joule seconds. It's pretty small. This thing with the slash through it is actually equal to h over 2 pi. And so that's equal to 1.05 times 10 to the minus 34 joule seconds. And this has a name. It's called h bar because of that slash through it. And all the usual things that we talked about with electrons and nuclei apply to this too. Get to a higher state by absorbing photons or by collisional excitation. Get to a lower state by emitting photons. All the same stuff. So let's apply it a little bit. So we've got a molecule, 2 atoms connected by a spring. There's 2 atoms connected by a chemical bond, so we've got one of our mass spring systems here. And let's suppose that we know that it requires 0.05 electron volts energy input to raise this molecule from its vibrational ground state. Okay, ground state is of course the bottom, to the first vibrational first excited state. So how much energy is required to raise it from the first excited state to the second excited state? Okay, answer 3. It's exactly the same, and that's correct. Why is that correct? Because we said that the spacing of the energy levels is exactly the same, isn't it? So if this was 0.05 eV, that's going to be 0.05 eV, and that's going to be 0.05 eV, etc., etc., etc. Now notice that these energies are actually a lot smaller than the energies we've been talking about to excite the electronic states of atoms, these vibrational energies. We're talking about a tenth of an eV here, and we were talking about 10 eV for the electrons. Okay, so let's consider two different diatomic molecules. The first one, molecule A, has 2 atoms of the same mass, Ma, and molecule B has 2 atoms of whose mass is each 4 times as great, and the interatomic bond stiffness is about the same. So which one has vibrational energy levels spaced closer together? Okay, it looks like answer 2 is popular. It says B would have levels that are spaced closer together. Why would that be true? Okay, this number's the same, but you're dividing by a bigger number here. So the energy spacing would indeed be smaller. The energy levels would be closer together. This molecule might have energy levels that looked something like this. But they'd still be the same spacing. Okay, good.